In this lecture, we will talk about capacitor charge balance. This slide comes from the previous lecture. We know that the differential equation for the capacitor I sub c equals to c times dV over dt. The total charge is the integral of capacitor current over time plus the initial charge Q sub 0. The capacitor voltage equals to 1 over c times the integral of capacitor current over time plus the initial voltage V0, also equals to Q over C plus V0, where Q is the total charge into the capacitor and V0 is the initial voltage. Please remember this equation, and we are going to use it in the LTspice simulation for analysis. So now let's run some LTspice simulation. The first example is a current step into a capacitor. For simplicity, we use an ideal capacitor. So this is the basic setup and discussion about this simulation. We have a current source I1 as a pulse current into the capacitor C1, which is 100 microfarad. Current I1 provides electric charge Q into the capacitor. As we know, a capacitor behaves like a voltage source. That means the voltage over the capacitor cannot change abruptly. The voltage slope dV over dt equals to I over C. If we have the current, in this case, is 1 amp step, so that means the current is changing from 0 amp to 1 amp and stay there. The power is coming from the current source into the capacitor, and the power flow is from current source to capacitor. This is the important equation we just showing here. V equals to Q over C plus the initial voltage. So this is the simulation results. The 1 amp current step is run for 1 millisecond. The trace in red is the current into the capacitor. The green waveform shows the capacitor voltage. You can see from time 0 all the way up to 1 millisecond, capacitor voltage has a positive slope, which can be found as I over C. So that's 1 amp over 100 microfarad equals to 10 volt per millisecond. You can see that at 1 millisecond, the voltage of capacitor is reaching 10 volt. In this example, the current source becomes a pulse waveform. So this is the detailed definition about this balanced current pulse. The current pulse has -1 amp to 1 amp pulse. The duty cycle is 50%, and the frequency is 100 kHz. This current pulse will feed into the capacitor, and we're gonna check the capacitor voltage. Because the current has average 0 amps, that means the average current charge into the capacitor over a switching frequency is 0. This is the transient simulation results. In this case, the current is ±1 amp at 50% duty cycle. That means at steady state, the capacitor charge is balanced over a switching cycle, and Q is 0 over a switching cycle. In this case, we can see the blue waveform shows the power into the capacitor. You can see the average power is 0 watts, and the power is going up and down. That means the power is into the capacitor and out of the capacitor. Look at the second plot. We have the capacitor current in green. This is the current from the current pulse I1. It's changing from 1 amp to -1 amp with 50% duty cycle. The capacitor voltage is in red. When the capacitor current is positive, the voltage rises up, reaching the peak at 50 millivolt. And at that moment, for example 5 microsecond, the capacitor current changes the direction, becomes -1 amp. That means the charge is out of the capacitor back into the current source I1. In this case, the V out or voltage over the capacitor drops until it hits 0 and rises up again. So this behavior is at 100 kHz. Here is another example. In this case, the capacitor charge is unbalanced. Q is now 0 over a switching cycle. In this particular case, we have 100 kHz current pulse, but the duty cycle becomes 80%. That means over a switching cycle, we have positive charge into the capacitor. We expect to see the voltage increase over this capacitor. Here is the transient simulation results. On the first plot, we have the positive average power into the capacitor. And on the second plot, the current is changing from 1 amp to minus 1 amp, but we have positive duty cycle, which is 80%. That means we put more charge over the capacitor voltage. And notice that the capacitor voltage in red gradually increases over each switching cycle. Recap. In this lecture, we talk about the charge into the capacitor. We understand that the charge equation equals to the integral of capacitor current over time plus the initial charge. If the capacitor charge is balanced over a switching cycle, we understand that the capacitor voltage will become to the initial voltage. However, unbalanced charge over the capacitor can cause capacitor voltage increase or decrease. Capacitor charge balance is the key of the steady-state analysis for analog circuits and also for the switch mode power supply design. We did some simulation in LTspice and showed you the transient simulation results. Thank you and see you next time.